Hi, this is Tzvi Rosen with another lecture in our online course on matrix theory. And in this lecture, we'll be talking about matrix transformations, which is a way of reinterpreting everything we've been doing with matrices as functions, which take some input and provide some output. And the inputs and outputs that we're going to be talking about are vectors. Okay, so in general, in our course, we're going to be looking at vectors in Rn. Okay, this describes ordered sets of real numbers. Up to xn, so it's a list of n numbers in that order, and each of the xi's is a real number for all I. Okay? And you might also see these as, so this is called the row vector notation, and you can also see this as x1, x2, down to xn. This is column vector notation. Okay. And these are vectors. Okay. When we're working in Rn, so for a fixed n, there are special distinguished vectors called standard basis vectors. So Rn has n special vectors, and these are the ones that have 1 in one of the positions and zeros everywhere else. So for example, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, etc., all the way to 0, 0, 0, 1. Okay? Now this vector is called E1, or the first standard basis vector. Okay, so these are called standard basis vectors. Okay, this vector is called E2, or the second standard basis vector. And then this one is called En. That's the nth standard basis vector. Okay, so the vectors are going to be the inputs and outputs of our function. So let's recall some notation from the study of functions. So when we talk about the image, when we have a function f, which maps some set A to some set B, so these are inputs, and these are outputs. The image describes the output of a function when you evaluate it at a certain input. So if f of A equals B, then we say that B is the image of A. Okay? Domain, in this context, it describes A. Okay, in this example, it's A. Generally speaking, it's the set of inputs for the function. Okay. The codomain is, in this example, is B. B is the codomain. It's the set that f is defined as mapping to. Maps to. Okay, but not everything in the codomain necessarily is the image of something in the domain. The subset of elements which are the image of things in the domain is the range. So the range is the subset of B, which are images, in the sense we just described, of elements in the domain. Okay, so these are 4 terms that we should be familiar with, and let's see how they're used in the context of a specific example. Let's say f is the function taking the real numbers to the real numbers by sending a number x to its square. Okay, well then, if we're looking at a specific element, we could say that the image of -1 is +1. Okay. As for the domain, it's the first set here. The codomain will be the second set. That goes here. As for the range, this is the subset of elements that are images. So I know there's not going to be any squares that are negative here. So this will be all positive, all non-negative numbers. So this is all numbers in R that are not negative. Alternatively, you could describe it as the interval 0 to infinity. Again, this is describing the range, the elements that are actually the images of something in A, in the domain. Okay. Now let's talk about transformations. So transformations are functions from one vector space to another. So T mapping Rn to Rm. Okay? And an example of that might be T evaluated at the vector x1, x2, x3 goes to a vector x1, x2, x3, and x1 squared plus x2 squared plus x3 squared. Okay? This would be an example of a transformation because it's a function mapping one vector space to another. And we should specify which vector spaces those are. So this would be T from R3 to R2 because there are 3 coordinates in the input and then 2 coordinates in the output. If we have the special case that m equals n, then we'll say that T is not just a transformation, but it's an operator. Okay, so this first case is transformations. And in this special case, we call it an operator. Okay. And an example of that would be something like T of the vector x1, x2 will give us the output x1 times x2 and x1 minus x2. Okay, and the input is from R2, and the output is from R2. Okay, so in this case, m equals n equals 2. Okay. Now we can focus on matrix transformations. So these are special transformations which can be described by a matrix. Okay, so T is a matrix transformation if T of x, and let's give it a vector. Let's give it a domain and a codomain, Rn to Rm, is a matrix transformation if T of x can be written as A times x for some m by n matrix A. Okay, so an example of this would be if you have, let's say, T from R2, or from R3 to R2, which can be described as follows: T of x, y, z equals W1, W2, where W1 equals 3x minus 5y plus 2.6z, and W2 is equal to x plus y. Okay? Then I can also describe this, instead of as a transformation, I can describe it as a matrix multiplication. Specifically, 3 minus 5, 2.6, 1, 1, 0, times x, y, z equals the output W1, W2. So these are my inputs, and this is my output. Right? We have a vector with 3 coordinates as the input, and a vector with 2 coordinates as the output. There's a property that we really like transformations to have called linearity. Okay? And a linear transformation is one that satisfies the 2 following properties. So first of all, or let's write it out. A transformation T from Rn to Rm is linear if, first of all, multiplying a vector by a scalar. So let's let x be a vector and k be a scalar. Okay, and we'll make this a little bolder so you know it's a vector. Then T of k x has to be equal to k times T of x. So I can, when I want to know what the value of the transformation is at a certain vector, it'll be the same no matter, so multiplying that vector by something, it will affect the output just by multiplying it by the same amount. So if you multiply your input by 2, you might as well just hold off and multiply the output by 2, and it'll give you the same thing. Okay? Okay, and the other property that we would really like to have is if we have 2 vectors, x and y, then T of x plus y will be equal to T of x plus T of y. Okay? And this is saying that I can add the inputs together and then do the transformation, or I can do the transformation on both separately and then add them on the other side. Okay? And that'll give me the same result. So a quick example of some linear transformations you should be familiar with. So first of all, the 0 transformation. which sends every vector to 0, is actually a linear transformation. So 0 equals the 0 vector, vector of all zeros in whatever vector space you're mapping to. This is a linear transformation. Another linear transformation is the identity, okay, which takes whatever vector you put in and spits back a vector. That's certainly linear. T of x equals x is linear. But not all transformations are linear. So some examples of nonlinear transformations are the ones we saw earlier, multiplying things together. So T of x1, x2 equals x1, x2. So that this would just be a map from R2 to R1. So this is not linear. How can we tell? Well, if I did twice this vector, so that multiplies both coordinates by 2, then the output would be 2x1 times 2x2, because that's how you get from inputs to outputs. You just multiply them together. But that's 4 times x1, x2. So on the one hand, we were multiplying the input by t of 2x. Okay, on the other hand, so we have 4 here, and we have an input multiplied by 2. Since those don't match up, that means it's not linear. Another example would be t of 1, 1. So if you take the vector 1, 1, this should be the same as the vector 1, 0 plus 0, 1. Okay, so this is a question mark, I guess. Or rather, no, that's not a question mark. That's true. The question mark comes when you ask, is this the same as if you were to apply it to each separately? T of 1, 0 plus t of 0, 1. But when you plug this into the function, you multiply those two coordinates together, both of these are going to be 0. However, if I were to evaluate the function from the start, that would be 1, because you multiply the coordinates together and you would get 1. So the other aspect of linearity also fails there. This must not be equal. So neither property of linearity holds. Okay. So the cool thing about linear transformations is that every linear transformation is really a matrix transformation. It's coming from a matrix somewhere. So given t from Rn to Rm, a linear transformation we can write a matrix A such that t of x is just given by matrix multiplication by x. Okay? And how do we get this matrix? It's really easy. All you do is you apply the linear transformation to each of your standard basis vectors. Okay? So A will be equal to t of e1. Okay, that will be a vector of length m. So you put that as the first column. Then t of e2, etc., all the way to t of en. Okay? And this will give you a matrix that you can multiply by your x to get the value of the transformation. And you can even see why this would be when you're looking at this. What happens when I multiply by the first standard basis vector? Okay, we'll do this in green because it's an example. So you have 1, 0, 0. Well, when you do this multiplication, this would give you only the first column, right? Because every time you're multiplying by every time you're multiplying by the later columns, you're picking up zeros. So the only column that shows up is the first column, and that's going to be t of e1. Okay, so plugging in e1 gives you t of e1, which is exactly what we want. Okay, and the same would hold for e2 and e3, etc. Okay. So let's look at an example of turning a transformation into a matrix associated to the transformation, or the standard matrix. So here's a matrix here's a linear transformation from t, which maps from R3, right, because there are 3 coordinates here, and the output is in R4 because there are 4 coordinates here. That means we should be looking for a 4 by 3 matrix. Okay? And the way that we get our matrix, we take t of e1, t of e2, and t of e3. Well, what's the value t of e1? That's what we would get if we evaluate t at 1, 0, 0. So t of 1, 0, 0, plugging that into the first coordinate, we would get 4. In the second, we would get x1 plus x2 is 1. x2 minus x3 would give us 0, and x1 minus x3 would give us 1. Okay, next up, we would get t of 0, 1, 0. This is the second standard basis vector. And that would give us 0 plus 1 is 1. 0 plus 1 is 1. 1 minus 0 is 1. And 0 minus 0 is 0. Okay, and finally, the third basis vector, we would have the x1 and x2 are 0, and x3 is 1. So we get 0 for our first coordinate, 0 for our second coordinate, minus 1 for our third coordinate, and minus 1 for our fourth coordinate. Okay, and so the result is that the matrix we're looking for is 4, 1, 0, 1, 1, 1, 1, 0, and 0, 0, minus 1, minus 1. Okay. Okay, so let's say I wanted to know what the value of t was on the vector let's do 5, 8, 13. Okay, so one way to go about that would be to plug it into the original formula. So I would say 4 times 5 plus 8 and 5 plus 8 and 8 minus 13 and 5 minus 13 will give us 28, 13, minus 5, and minus 8. Alternatively, I could just do a matrix multiplication, which would be 5, 8, 13. And multiplying the matrices, we would get 28, 13, minus 5, and minus 8. And obviously, this should not be surprising. We're basically doing the same thing in 2 different ways, but you can imagine that having it as a matrix in a way that you can program it into a computer, write it down really easily, could end up being really useful, especially since we have so many tools that we're developing to manipulate matrices. Okay, so let's look at some more examples. So we'll look at now at scaling in the plane. And what I mean by the plane is R2, you can think about R2 as pairs of real numbers that correspond to certain arrows, originating at 0, 0 and going to some point x, y. Okay? So this is 0, 0. This is x, y. And what we'd like to do is find a map T which goes from the plane to itself. And the way that it's going to act is it's going to take T of x, y and then scale it by some number. So let's say, let's start with 2. Let's keep it straightforward. Equals 2x, 2y. Okay, so what that's doing in terms of this picture, make it a bit bigger so it'll be easier to see. So what that would do is multiply this vector by 2. Okay. So it will scale up the whole picture. Okay. So if you have a different input here, let's make it over here. So then it'll multiply that one by 2 as well. Okay, so this will be a different vector. Let's call it x2, y2. Then the output of that would be 2x2, 2y2. Okay, well, how could I describe this as a matrix? It's quite simple, right? You just have to see what the values are on the standard basis vectors. So T of E1 and T of E2. Okay, if the basis vector is 1, 0, then when we scale that up by 2, we would get 2, 0. And the second basis vector is 0, 1, so we would get 0, 2. Okay, so this is the matrix associated to this transformation. It's 2's on the diagonal and 0's elsewhere. Another way of writing this would be 2 times the identity matrix of size 2 by 2. Okay? So that gives us a matrix which scales vectors in the plane. Okay? And in general, let's say we didn't want to scale it by 2. So let's call this A2. Let's say we want to scale it by an arbitrary constant k. Then we could take k on the diagonal and 0's over here, so that we're taking k times the identity matrix of size 2. Okay, cool. So we're relating these matrix transformations to geometric pictures of vectors changing shape. What about reflection in the plane? So let's say I'm going to fix the y-axis. And I want to reflect lines across this y-axis. Okay, so we're in R2 again. And now let's say we have a vector here, and let's make another vector here. Okay, and we want the outputs to be reflections across the y-axis. And let's make this slightly different color. Okay, so this will be, how can we write this down? Well, if this is let's call this x1, y1, then the output here, because we're reflecting across the y-axis, this y value shouldn't change, so that'll still be y1. but the x value flips to its negative. So this will be negative x1. Okay, and over here, if it's x2, y2, then we're going to get something similar, negative x2, y2. Okay, so when we're taking t of xy, it seems that what we're getting back is negative x, y. Okay, and when we want a matrix to represent this, we're going to have A equals value of on the first standard basis vector. So when we plug in 1, 0, we get back minus 1, 0. And when we plug in 0, 1, that doesn't change, so we get 0, 1. Okay, and this is the matrix associated to reflection across the y-axis. Next, we'll consider rotation in the plane. And here what we mean is that t of xy will be equal to the rotation of that vector, so rotation of the vector by theta degrees. Okay? So in particular, if we start with a vector that looks like this, we spin it around theta, and we get this. Okay? But this is a confusing function to write down. I wouldn't even know how to give you a formula. Instead, we're going to go straight to the matrix form. So a fact about this transformation that might be a bit complicated to prove is that this is actually linear. So t is linear, which means it will have a matrix associated to it. And what will that matrix be? It will be the columns that we would get after inputting the standard basis vector. So let's start with standard basis vector number 1, 1, 0, which is our E1. So when I rotate this by theta degrees, what's my new point here? Well, using trigonometry, the x-coordinate corresponds to cosine of theta, right? Because this is 1. This length is 1. So that means that this length is cosine theta. Meanwhile, this length is sine theta. Okay? So that means that the output from t of E1 is cosine theta, sine theta. How about t of E2? Well, here we're starting with 0, 1. This is E2. And we get theta degrees here. So what's our x and y coordinates? Well, again, we have that this length is cosine theta. So let me signify this here, cosine theta. And this length is going to be sine theta. Okay? But we can see that the cosine is going to be positive, whereas the sine is sticking to the left, so it's going to be negative. So let's write that down. So t of E2 is minus sine theta, because you have it going in the negative x direction, and cosine theta in the y direction. So that means our matrix A is cosine theta sine theta minus sine theta cosine theta. Okay, and that, if you want to know how you could rotate a vector by theta through the plane, this is how you do it. Now we can use this matrix to get a formula for the rotation of a vector. So t of xy will be given by cosine theta sine theta minus sine theta cosine theta times xy, which will have as output x times cosine theta minus y sine theta, x times sine theta plus y times cosine theta. And that's how you rotate a vector through theta degrees. And with that, thank you for attention, and I'll see you next time.